All right, guys, so this is going to be our first video where we start looking at the two-dimensionality, which really is the same as the forces and fields that we were doing before, except now there's 2 dimensions. Kind of like when we had forces in 2 dimensions back in Physics 1, or we had momentum in 2 directions. You just need to find the components and see how those balance. All right, so in this question it says that A and B both have a negative charge. So I'm just going to kind of label those. That guy's negative, this guy's negative, and then it says C and D both have a positive charge. All right, now the question is determine the electric field at the center. So we're trying to find out what is the electric field here. Now remember that electric field is going to be what would a positive charge do to the field of whatever it is we're looking at. So if we look at QA, let's start with QA there. So if we look at this guy right here, what would a positive charge do with respect to that? Well, a positive charge placed at the center would be attracted towards that, right? What about QB? A positive charge would be attracted towards QB, right? So that would be the electric field due to A, and that would be the electric field due to B. Now we're going to do the same thing with C and D. So if I look at C down here in the left corner, what would happen to a positive charge at the center? Well, it would be pushed away from QC. So the electric field due to C looks something like that. And then D, of course, would repel a positive charge also. So my electric field D would look something like that. So once we put it all together, we see that we've got 2 going up and to the left and 2 going up and to the right. Now, the horizontal components of those will cancel out, right? You've got the horizontal component going to the left for the A and the horizontal component going to the right for the B. Those 2 are going to cancel out because they have the same charge. Okay? The same thing will happen to the C and the D. The C has a horizontal component pushing over to the right, and the D has a horizontal component pushing over to the left. Those 2 are going to cancel out. So all of the horizontals are going to cancel out, leaving us with just the vertical for each of those 4 forces. And so when we add all those together, we should end up getting a vertical field that is very large and upwards, because every single one of these charges is going to have a bit of field going upwards. All right? And so letter A says using the symmetry, determine the direction. That's what we just did. We decided that it's going to go directly up. Okay? Now, for question B, it says calculate the magnitude of the electric field at the location of Q. So basically, we just need to find the electric field from each of those points, right? Now, if you're really smart about it, you'll recognize that the distance from QA to the center is the same as the distance from the Q to the QB, and from the Q to the QD, and from the Q to QC. So all of those distances are the same, right? You'll also recognize that they all have the same charge, right? Some are positive, some are negative, but the magnitude of the charge is the same. So really, if I can find the magnitude of one of those fields, then I can just multiply it by 4, and I should be able to get the answer, right? So that's what we're going to do. We're going to find the magnitude of the electric field of QA. All right? Now, the electric field, you can either do the force over Q, or you can just do KQ over R squared. Now, we do need to find that distance. It says in the problem that it's 5 centimeters on a side, right? So what that means is that we have 5 centimeters from one end to the other. So that's the square. We're not looking at the yellow square. That's just the border of the picture. The square is the square formed by those charges. So that's 5 centimeters, which means that half of that is 2.5 centimeters. And so across would be the same. So this would be another 2.5 centimeters. And so with that, we can get our hypotenuse. And our hypotenuse is 3.5 centimeters. And so now we have a radius there. So we can go ahead and do 9 times 10 to the 9th times the charge, which is 1 microcoulomb. And then we can put in our R, which is 0.035 meters, because we wanted it meters and squared. And now we should be able to calculate the electric field due to charge A. And I got 7.35 times 10 to the 6th. Now, what are the units there? Well, remember that the electric field is just the force per unit charge. So that's newtons per coulomb. All right, so now we've got the electric field due to A, but remember that the electric field due to A is up at an angle, right? It's up this way. And what we're interested in is the vertical. We talked about the fact that the horizontal pieces cancel out. So really what we're interested in here is the vertical component of this. So we've got that 7.35 times 10 to the 6 newtons per coulomb. That's the hypotenuse. Because of the shape of our square, we know that this is a 45-degree angle, right? Because it's a square and this is the center of the square, and we can take each of those 90-degree angles and chop it into 2. And so we should be able to find that side over there by doing the sine of 45 equals the opposite, which is what we're looking for, divided by the hypotenuse, 7.35 times 10 to the 6th. And that should then hopefully give us the value of the horizontal component of that electric field, which is 5.2 times 10 to the 6 newtons per coulomb. Now that is the vertical component of the electric field of QA. Now we already talked about how the total electric field is just going to be the sum of each of those 4 electric fields, which are all going to be identical because they're all going to be at that 45-degree angle. They're all at the same distance. They all have the same magnitude of charge. And so all we have to do is take that and multiply it by 4, and we get our final answer, which is that the total electric field on that Q is equal to 2.0 something, so 2.1 times 10 to the 7th newtons per coulomb. All right, and that's what we get for our final answer. So I hope that was helpful. Notice that the answer at the back of the book may be slightly different because of our rounding. If you keep all the digits and don't round, as I was rounding to 2 sig figs early on just to simplify the work here. But if you keep all the significant figures, all of the digits, then you should be able to get an answer similar to what's in the back of the book. This is pretty close. I think the back of the book says 2.04, so we're all good. That is the end of this question.